Okay, welcome back, everyone. So we will continue with the theme on neutral atoms, and now Harry Zhou will kind of go into more depth on how to do QEC in neutral atom quantum computers.
Thank you. So hello, everyone. I'm Harry Zhou from Harvard University and QuEra Computing, and I'm excited to kind of continue on the topic of neutral atoms and tell you a little bit more about kind of some considerations when trying to do quantum error correction with a view towards the future. I do want to emphasize that I tried to make it as also computer science friendly as possible. So if you're a computer scientist and there's something that you don't understand, find too physicsy, please interrupt me. And also if you're not a computer scientist, also feel free to interrupt. Okay, so we've heard in the previous talk that we're starting to witness this generation of new quantum systems in which we can really think about early fault-tolerant logical quantum processes. And I mean, here, if you look at kind of this diagram that Dolev showed in his talk, it really kind of reminds you a little bit already about what maybe some of the early classical computers might look like, with maybe a storage zone that looks somewhat reminiscent of a RAM in your system. You have kind of a computing region, various things. And so it's kind of interesting to think about how, as we go further in this field, how should we further develop the architectures, and what are some considerations for thinking about it, maybe at a more abstract level. So in today's talk, I'll try to give you just a very quick overview again of some of the high-level neutral atom operations. But at first, I'll actually try to describe it in kind of as minimal and simple of a way that nonetheless captures a lot of the things that we have done and that the natural operations that you might want to do as you start designing further error correction codes. So it's not quite Python level, but hopefully it's high level enough of a language. We'll then talk about that a little bit in the context of our proposals for implementing quantum LDPC codes. We have this proposal for hypergraph product codes, but I think there are also other interesting code families that people in the community have been thinking about. And then following that, we'll then move from thinking about the codes to thinking about the algorithms and thinking about how we kind of take these same native tools and do it in the context of, for example, transversal gates that you've already heard a little bit about throughout this conference. After that, then I'll go kind of into the more lower level details of the neutral atom system. So you might think of that as maybe a little bit more like an assembly model, details of really if you tried to do all of the kind of things behind, what are the microscopic operations, which give you a little bit more flexibility than these high-level operations that I'll talk about at the beginning. And finally, I was also asked by the organizers to maybe give just like a little bit of a perspective or peek view of where the field might go. This is also something that we would like to know. So it's definitely something that is very under development. I think the nice thing about the neutral atom field is that it's an extremely vibrant field in both academia and industry. And so it will be kind of just an overview of a few things that people are thinking about. But I'm sure that there will be many other interesting things that I won't have covered here that we'll be hearing about in the next couple of years. Great. So we already heard from Dolev a little bit how these neutral atom systems work. I'll maybe just give a very quick overview of some of the key operations again, but focusing kind of at like a high level kind of a block operation, if you will. So a very simple model that you might have in mind, this is not the most general model, but a very simple model might be that you kind of have a rectangular array of sites and qubits. In practice, it doesn't have to be rectangular, but for simplicity, let's just say that for now. And then kind of a very natural operation that we can do is, so we have some of these sites and some of these qubits. Some of the sites might already have atoms, like here, or have qubits if you want. Some of the sites might be empty at this point. So what you can do is essentially take any rectangular subarray of qubits, and with bad PowerPoint animation, you can kind of move it over to some of the other empty sites, okay? So that's kind of a very natural operation. Maybe some of the key things to highlight here. First is that we're kind of working with, in this particular case, a rectangular array, but also, more importantly, the array that we move has this rectangular structure, right? So there's a very clear structure. Fundamentally, it comes from the types of optical tools that we're currently using, but really this is kind of what's efficient for us to do, okay? Pick up some rectangular subarray, move it to somewhere else, and then do operations. So what operations might we want to do? Obviously, kind of the most interesting one in many cases is the 2-qubit gate. So in this case, what we can do is we move some subarray such that they're neighboring some qubits, and then if they are within this kind of entangling region, and if they are next to each other, then they'll do a 2-qubit gate. These also generalize to other types of gates. Kind of if you want to do 3-qubit gates, you can kind of somewhat imagine the same thing. But this is maybe the most relevant also for error correction. Okay? Yeah.
So it's also very general. Like if you really didn't want rectangular subarray, is it easy to also do just an arbitrary subset of locations that move them?
Yeah, so I guess these two are really somewhat kind of decoupled. The gate is basically as long as they're neighboring, they'll do it. So if you kind of pick them up and put them there, then there's the separate question of if you wanted to move, can you move in a different grid? I think it's very likely that in a few years, people will come up with other clever optical tools or manipulation methods. This is kind of a constraint that is just, I would say, with the current generation. Another thing maybe to also mention here is that in principle, you could kind of go one by one and like move this atom over to where you want arbitrarily. So in principle, you can do anything. It's just that doing that anything right now might not be the most efficient. But again, I would say that, and this is also something that I'll return to later, I think a lot of these types of things, right now, there's a lot of creativity in the community. And so if you have a good reason for not wanting to do just a very structured thing, but do something else, and it gives you like a huge improvement, people will definitely try to find ways to make that reality. Yeah. Great. OK, so we now know how to do the gates. We now know how to configure things. And so really, I think one of maybe the key things to remember from these two slides of what the native operations are is that there are kind of, at the moment at least, very clear structures in the native control-efficient operations that we can support. I talked about this rectangular subarray. Really, one way to maybe phrase it in a language that will be, I think, a little bit evocative of kind of some of the code constructions that we'll see later is that it's kind of like a product, right? So if you have something that is rectangular, one way to see it is that you have two 1D things and you take a product. And that's how kind of a lot of these current tools are formed. But again, this is something that we just have in the current generation. OK? So how does this relate to QEC codes? For that, I'll just maybe give one very quick review of quantum error correction here, so just to set the stage. So typically, we care about these quantum codes characterized usually by these NKD parameters, number of physical qubits. Usually, people refer to the number of data qubits used here. Number of logical qubits, code distance. And in general, the target or the name of the game, at least in terms of the code design, is we want as large K and D as possible, so as large kind of encoding rate and large distance up to a certain point based on how much error suppression you want, while having as small of an n as possible. So you want to use as few physical qubit resources to do what you want. Now, of course, we've heard already in quite a few talks about these bounds if you have just a 2D local system and you can't do much better than this well-known surface code that I won't go into detail here. But of course, there's been a lot of amazing work about how you can actually have better codes, even kind of these so-called good quantum LDPC codes, with like much better parameters, where instead of being constrained by this, you can have both the number of encoded qubits and the distance scaling linearly with the system size. However, it's also known by some very nice work from Neuden and Arni and others that kind of these types of codes, if you generalize them, if you generalize some of the previous bounds, there are kind of constraints on how much known locality you need. And it seems like you need actually substantial known locality. So in the neutral atom case, there is this flexibility of moving the atoms around. This is kind of an earlier generation video in which the toric code, this is kind of roughly speaking in the quantum error correction language, one round of Z syndrome extraction for the toric code. So non-local connectivity is definitely possible with neutral atoms, but the question is it really compatible with this parallel efficient control that we like, right? This is really the key thing that enabled all of the cool experiments that you heard in Dolev's talk, and I think it's something that is quite powerful as we think about going to larger systems. So for quantum LDPC codes, there are these codes that can have much higher rate. But if you think about what they look like, or if you ask Dali to tell you what they look like if you didn't know, it might look something pretty random. I think Yoshka also had some very nice illustrations in his talk about kind of if you just naively draw a lot of the diagrams, the whole jumbled mess that it looks like. And arbitrary connectivity may not be efficient to implement, right? I mean, in some cases, maybe if you have some kind of clever compilation tricks, maybe you can get somewhere. But I think it's fair to say that with this kind of rectangular constraints, it's not obvious if you want to implement something that is like generic all-to-all arbitrary connectivity, at least at this point. So really the key is to identify the right types of structures that allow you to do something a little bit more. And I think what we heard from Ted's talk earlier in the week is also a very nice example of this, as well as I think Oscar also mentioned, of trying to understand the structure and trying to see how those actually match with the possible constraints that you might have. So one kind of particular example that we found and that we really like is this hypergraph product code. So this has been introduced a few times. I'll just go over it very quickly again. So we have a classical code as illustrated here by kind of these rectangular checks and these classical bits here. And these connections, I'm just schematically drawing. This just means that this check will involve the parity of this bit. So if that bit number 5 gets flipped, then this check bit will kind of flag up. Okay. So for the hypergraph product construction, what we're going to do is we're going to take 2 classical codes and then take some type of product between them. So the first thing to specify is where the data qubits are. So we have these data qubits here, which essentially lie on these kind of intersections of a check qubit, classical check, and on the 2 sides, or a classical data bit on the 2 sides. With this, we'll have some number of data qubits that, roughly speaking, is kind of on the order of n squared, where n is the classical number of bits. And then we'll also define the checks. So the x stabilizers will be these intersections of classical checks and classical bits. And then the z stabilizers the other direction. And then what we're going to do is going to inherit all of the connections from the classical code. So this is very important because you immediately see that this kind of aspect of you inheriting the connections in the QEC code immediately gives rise to a clear product structure that is also something that we can now start to think about utilizing. Just in terms of code parameters, if you use good classical codes, which have a number of encoded logical qubits and distance, both scaling linearly with the number of physical qubits, then you'll end up with a quantum code that has a linear number of encoded qubits and a distance that scales as the square root. So if we compare this to the surface code, you'll see that we still have the square root distance scaling with maybe a little bit less good prefactors, but more importantly, we win in this encoding rate. And I should also mention that this type of idea really kind of was the beginning of this whole sequence of improvements that eventually led to the good codes. So these good codes, in some sense, they're also kind of inspired by these original simpler product type structures. Okay, great. So now we can go back and think about how we implement them. And I think I've kind of already told you, essentially, we want to match the product structure of these codes with the product structure of the optical tools. They both have product in their name, so probably they're the same thing. And indeed, what we can do is we essentially implement parallel row permutations. First, this allows us to kind of in parallel implement all of these connectivities like this. And then we can do the same thing in the vertical direction. Now here, the types of connectivity that we might have in each of the classical codes, however, is quite generic, right? So So these are just some good classical codes that typically people might construct using kind of just some like random construction. So for the 1D, actually, we do need to have more general connectivity. We're utilizing the product structure to gain a lot of mileage and make it work for the quantum codes. But we still need to implement potentially an arbitrary kind of connectivity within the one dimension. So if you think about this actually is also not too difficult to do in a pretty efficient manner. So we can actually do a one-dimensional sorting network. The constraints are a little bit different from your usual computer science sorting networks because we're trying to move things in parallel. But nonetheless, you still get a log depth. And this, you might not be too surprised if you think about the computer kind of science or your algorithms class. Essentially, you do a divide and conquer algorithm where you kind of take the qubits that you want to end up on the right side. You move them all out to the right. And then you can kind of just compact the workspace a little bit and recurse, right? So in one round, we've kind of done like half of the work, and then we go down one layer more. And so the number of layers that we need is a log depth. And so this gives us an algorithm to implement arbitrary sorting in 1D to implement our desired connectivity using a log number of layers. And then we take the product, we'll get still a log number. Yes?
So as you move in this log depth, you have to like transfer atoms from the two AODs in every step, or is it just once? Or
yeah, so in this particular construction, you do indeed need to transfer. You can, I think, yeah, like one step of this, if I remember correctly, is like one transfer in and out. This is something that one can definitely try to optimize if you're given a particular one. And for small instances, you typically can kind of cut quite a bit relative to this. Yeah, so this is something that actually might also be interesting, and I'll mention this in kind of the open questions part. Maybe there's better ways to design the codes such that you minimize metrics like that or like other ones. Yes.
So the moving time required to measure all the checks for a given hyperproduct code would be just like log n plus log n, because you do like row permutation. And
yeah, roughly speaking, exactly. So I'm going to show you a movie next of how this works. You've already seen a lot of movies, so I decided to add some sound to this one. So you can see that we're kind of doing this log depth sorting network here. And so that's one gate. Then you do the same thing for the second round. It is right now quite a bit of moves, but nonetheless, it's still a log depth. And so if you go to a much larger one, it actually will still roughly be like this. Maybe I'll turn the volume down a bit.
How big is this code?
This particular one, I think, was, so I guess this is like how many? So this is 15 in total. So I guess it's like 200 or so, including both data and Scylla. The classical code, I think, is like a, I don't remember the exact parameters. It's been a while since I made this, but yeah. Right, so yeah, so you can see very clearly from this that taking the product and the 1D log depth rearrangement, you can get kind of these implementations of the syndrome rounds of the hypergraph product code. And this is kind of like the fundamental building block also if you want to then go and do other stuff like gate operations and whatnot. I think some of the things also to mention here, maybe towards kind of the practical implementation, it's actually a cool observation made in this nice paper from Yale, and also I think Chris also in parallel had some similar ideas, that this particular way of doing it, where we're actually only using a single ancilla for the syndrome extraction, is actually fault tolerant. I won't go through the details of this. It relies a little bit on the row and column structure. So actually using this, you can already still get most of your code distance, which is very nice. And I think that's part of the reason why both in the numerics that we did, as well as some of the earlier work from Michael, Nicola, and Maxime Tremblay, we saw relatively good performance. So we can now actually go and do the circuit level simulations and try to compare what the resources are. I'll just give you kind of the end result of that without going into too much of the details. So essentially, we can try to compare an implementation, in this particular case, just of the memory, using different types of families of quantum LDPC codes. So in this particular case, we looked at both these hypergraph product codes that I just talked about, as well as some lifted product codes for the smaller sizes. And we see that, for example, if you just compare even relatively modest sizes, you can still get pretty good performance. And around maybe 1,000 or so qubits, you can start to see improvements over the surface code that are kind of around an order of magnitude. Yes?
In these numerics, did you account for the fact that every time you transfer atoms to AODs, you get about 0.1% loss or something?
In this one, we didn't. I would also maybe say that this 0.1% is kind of a current number, and definitely can be improved in the future.
And how does that, what changes would you do to improve it, and like how low can you get it? And what are the costs associated with reducing it further?
Yeah, I think right now, I mean, Dolev can also chime in, but right now I think a lot of it is really limited by our patience in terms of like just aligning things well, like making sure that the traps overlap perfectly. If they're a little bit offset, then you could imagine you kind of like they slosh around when you try to pick up. Yeah, so I would say, yeah, I don't know if you want to
limited by patience, yeah. I mean, some of the sites can be like perfect. So yeah, I agree.
Yeah.
Yeah. The different question. So can you give us a feel with one example size how many moves there were to do like a full extraction time?
Yeah, so I think what you saw earlier was kind of a typical, basically what we were essentially simulating. Indeed, yeah. So I think, so I guess for example, if you have like a instance that is say like 50 or so, then you take the log of that and then you multiply by I think either 2 or 3 is the prefactor. So it'll be 3, let's say 3 log 50 of layers, which log base 250 is like 6, right? So like 20 layers. Yeah.
20 and so 20 layers to implement a size like 2,000 and
Yeah.
to go.
Yeah, and it grows pretty slowly as you go to larger sizes. Yeah.
Thanks.
Great. Yeah, so if you look at the numbers, I think they look very nice. And of course, I should also mention that most of these improvements are also very compatible with, for example, if you have Ytterbium where you can do erasure like Shruti has been pioneering, then I think a lot of these can really kind of combine and you'll get even more savings. Yeah.
Just like if it's about like a 20 rounds of moving, then it sounds like it's about, I don't know, like a 0.2% of the coherence time. Am I right?
Yeah, sounds about right. Yeah.
Then the
So it's maybe a little bit less than that. I guess when you're comparing also, typically you should think about kind of between the 2 gates, how long the time you move, right? Because that will set the idle error rate that you put in. And this is what we put in here. We were assuming definitely the simulations were with numbers that have been achieved in the community, but are not current numbers for our system. But also, I mean, if we're actually looking at 10,000 atoms, right, that's still something that is in the future. So I think when we look at these extrapolations, we're really having that in mind, that some of these can kind of be combined. And also, I think some of the ideas, like with the hierarchical codes, you could also imagine combining some of these if you're a little bit worried about just the kind of these idle error rates and whatnot. Yeah, so this can potentially give you an order of magnitude saving. But also what we would really like to do is also logical operations. So we heard some very nice talks, I think also from Amanda yesterday. So the particular scheme that we had in mind here, mostly just for simplicity, because kind of once you have the surface code, then you can do the universal computation. In this particular case, was to teleport it out through an ancilla into another surface code. This is inspired by this Cohen et al. Scheme that was very nicely proposed from Sydney. And in this particular case, we slightly modify the construction such that you kind of save a little bit on the spatial footprint. So we ran the same circuit level simulations, and I think it was quite encouraging to find that actually you still get pretty comparable thresholds as the regular memory case, which a priori might not necessarily be what you expect, because these 2 codes, the LDPC code, which typically has a lot of expansion, might look quite different from the surface code, which is kind of this local and like somewhat topological. But nonetheless, the numerics were still encouraging as a starting point, and I think it will be interesting to see kind of future improvements to this. So I also want to mention that actually this is not the only natural family that you can try to implement. So in this very nice bivariate bicycle code construction from IBM that we heard from Ted earlier this week, I guess I won't maybe go into the details of the construction again. I'll just very quickly illustrate at a slightly higher level what you need to do. So you have kind of these like two different types of data qubits, as well as some different types of ancilla qubits. For the classical coding theory people, maybe think of this as it being like a quasi-cyclic code. And so there is these types of quasi-cyclic structures that are a little bit reminiscent of translational structures. So after seeing that paper, actually, we kind of immediately realized that there was a natural matching where you kind of just like shift it. And there's very nice work from Fred Chong's group that also further formalizes this and analyzes in quite a bit of detail, kind of teleporting in and out and whatnot. So I think it's something that is also easy for this, where the clear translational structure makes it well matched to the platform. And this is another movie. I forgot to add the music. So yeah, you can kind of see that it's like doing the translations and going around. Yeah. OK, so I think there's still a lot of interesting work to be done here. And I'll just mention a couple of maybe challenges and open questions for people to ponder about. So one thing is to better understand the fault tolerance in the general setting. We now know that for this simple hypergraph product, things are fault tolerant. But I think for other types of families, as well as even for the IBM codes, I don't know if we necessarily have a systematic understanding of why and when it's fault tolerant. Improving decoders is certainly a very important thing. And I'm very excited about Yoshka's new library. Hopefully, it can make it both faster, but also better. And I think thinking about ideas of really kind of porting over some of the ideas that we know well in other settings to the setting of LDPC codes, either from the classical literature or from other quantum codes, I think would be very interesting. Logical operations is definitely something that still needs to be improved. We have these huge blocks, and it's very difficult to act on them individually. And then also, I think, as we now think about these, I think it's also nice to just keep in mind the possibility of further co-designing the codes and the native operations that we have in this platform. Great. Any more questions before I move on? Yeah.
I do understand correctly that you can, for a hypergraph product code, you do sequential Z and X measurement. And for each stabilizer measurement, it takes you something like W log W steps to do it, where W is how big the weight of that operator.
Yeah, so maybe first about the sequential. So I think in the simulations, we were simulating sequential. But actually, if you look at the paper, there's also what we call a pipelined product coloration circuit. Essentially, the idea is, so there are constraints on like the X and Z, and that's why oftentimes you end up doing them sequentially. What you can do is you first do the first round of X, and then when you're halfway through, you bring in the Z's. And then now you can actually do that Z with that X simultaneously. So you kind of stagger them a little bit. I think there's very similar tricks also. I think in Oscar's hyperbolic Floquet paper, there was actually a similar way of kind of pipelining these types of things. So that's one comment. You don't have to have them fully sequential if you're doing like several rounds. The second comment regarding how to count kind of the depth. So indeed, it will scale with the stabilizer weight. Actually, I guess it scales with kind of the maximal qubit degree, right? Which, for example, if you construct the hypergraph product code from 3 full, then it will be 8. And then on top of that, it will be log the system size. So not log W, but log L. Yeah.
But for the bivariate codes from Bravo et al., there you don't have the log factor.
Exactly.
And when we're implementing the codes, is the dominant time waiting for the movement to actually occur, and the gate times are relatively quick?
Correct.
So then does that mean that we'll also need to explore trade-offs between movement speed and the fidelity of our overall code?
I think that could be interesting to look at as well. And I guess this really depends a little bit on what regime you're working in. Maybe right now, as Dolev also mentioned, we're not maybe so immediately worried about the movement speed. But certainly, as we think about these architectures in the long run, this is definitely something that is maybe a little bit open. Yeah.
And do we have a good sense of the relationship between movement speed and noise effects? Like, is it linear or is it quadratic in the speed, for example?
I would say to leading order, it's mostly just proportional to the amount of time that you move. And maybe this is a little bit more detailed physics, but the move time actually in the regimes that we operate in roughly scales as the square root of the distance. The way to think about it is kind of you have heuristically, it's like a constant acceleration. You kind of accelerate, then deaccelerate.
Like parabola.
Yeah, exactly. Yeah.
Is the qubit coherence time, is it something inherent to the qubit or something that can be improved?
It definitely is something that can be improved. So Dolev mentioned like 1 or 2 seconds. If we don't move, probably at this point, I would guess it's maybe closer to 10 seconds or so. I guess we have some atom computing people here. They've also very nicely shown coherence times that can be as long as maybe 50 seconds, I think. And that was even just with single pi pulse decoupling and nothing fancy. Yeah, so I think definitely there's still quite a bit of room to improve, especially if we're trying to do these systems well. Yeah.
So when you say constant acceleration, I would imagine that also depends on the track depth.
Yes.
Because
Yeah.
if it's too shallow, then you can't keep up the constant acceleration.
Definitely.
Okay, so there's a limit.
There will be some scaling with that, and definitely you need to trade off all of these factors. If you like had tons of tweezers, maybe you had them shallower, but then you can't move as fast. Yeah.
When you do the 1D sorting, how far do you have to go around the other qubits in the other direction to avoid the track merging?
Or you mean like the vertical offset, for example?
Right. Yeah.
Yeah. I mean, I think typically around like kind of 1 or 2 microns is already sufficient, especially if kind of they're just like relatively quickly moving past. Yeah, maybe 2 microns. Yeah, but it's definitely kind of more than enough workspace between offsets. Yeah. Great. Okay. So I'll go a little bit faster in this next section. Kind of ultimately, we're interested in not just implementing kind of quantum codes. Really, our grand target here is doing the kind of actual computation, right? And so a natural question is, when we think about computations, are there ways that we can also improve things using these native operations? And you already heard a lot about this in Dolev's talk, where you can kind of implement transversal gates by naturally just directly grabbing onto an entire logical qubit and then doing operations with that. And I think most of these, I think, were also in Dolev's talk, so I'll go quickly through them. For transversal gates, the nice thing is that the error, because you're kind of just matching qubits from the 2 different code patches, the errors actually don't spread within a code block. So that typically helps with the fault tolerance. But one thing that maybe wasn't studied quite as much in the previous literature was when you actually start doing this, how does it look like in an algorithm? And how do you decode it, right? So I think a lot of the early discussions was, oh, it's nice, we can do transversal gates, but it's actually surprisingly difficult to find works on kind of actually trying to decode them. I think there was some very nice work from Michael and Alex analyzing this, but it's not something that people have really looked at that much in earnest. And here really, kind of, you might imagine that now when you're trying to run an algorithm, you had a physical error kind of in the first logical qubit, and you just did a bunch of C0s, then this will kind of spread over to all of these other logical qubits, right? So if we're not careful, and if we're kind of not doing the decoding well, then we might actually need to worry about this massive error buildup. But the key thing is that here really kind of there was this one error event, and you kind of know that this error event is propagating in a deterministic way across this circuit. So this is really information that you actually have, and you should try to utilize that to improve your decoding. Maybe one comment that I really liked was Craig Gidney left a comment on when Scott Aronson was kind of discussing this, and he said that doing correlated decoding is not a bug. It's, I think, either he's called it a feature or competency, maybe even. Competence, okay, yeah. So I think this is something that, since you know that it happened, you should be doing it, right? Like you're going to run the same circuit, you're going to improve the decoding, and so then we should be doing that. And so this is something that we've been looking at in quite a little bit more detail. Maddie is the main theorist leading this, and also Chen from QuEra has also been doing a lot of the work. And essentially, the main challenge here is that for this decoding problem, there's actually it's inherently a hypergraph decoding problem. I won't go through the details of where exactly it comes from. I'll just say that unlike the usual surface code decoding problem, where you can typically decompose things into weight 2 edges, and therefore it becomes like a graph. Here, there are some graphs that are not decomposable into weight 1 or 2, at least if you just naively do it. And this causes it to inherently be a hypergraph problem that you're trying to solve. So we took 2 different approaches to try to decode this. One is to just do a most likely error decoding. Essentially, you phrase it as an optimization problem and throw it into your favorite integer programming solver. And then the other one, which I also won't talk about the details here, but I'll just mention that it's inspired by this union find algorithm that's for the surface code. And Nicola, Michael, and Vivian Londe had a very nice paper that analyzed some of the theoretical properties of this decoder earlier. And so using this, and I should also mention that there are many other possible approaches.
Sorry, guys.
Yeah.
When you try to do union, color code
yeah.
down to the hypergraph,
yeah.
you try to do union find on the color code without having the surface codes, you get bad results. So what is it about this problem that lets me go with a hypergraph?
So I would say that we're also not necessarily getting that great results with the union find here. And I think thinking of better ways to improve that is a great research question. Yeah. So you'll see maybe in I think the next slide that there is still a performance gap from the most likely. Okay. So a simple thing that we can do is to just do this simple circuit where you maybe choose to put some noise before or after the C0, and then you can see that if you just do matching independently, then essentially if the errors are mostly after the mostly before the C0, then down here you'll get double the error rate. So you're going to get a threshold that is roughly half your usual threshold. Whereas if you do the correlated decoding, then you recover some threshold that is much closer to the one that with all of the errors just after. What we can also do now is then look at a little bit deeper. Yeah. Yeah. So what we can also look at now is a little bit deeper circuits. So here what we have is 4 logical qubits and depth 32. What we're doing is doing one round of operations and then following that by some undetermined rounds of syndrome extraction that we vary. So for example, if you do D rounds, then you'll return to the usual setting, but you can also look at, as you reduce that, where does it really start to turn around? And what we see is that you can actually still get pretty competitive thresholds for this, even if you're doing just 1 round per C0. Okay, so we have a pretty deep circuit here, and then we measure them, and then with just 1 round per C0 in this deep circuit, we still have a threshold. And I would say these thresholds that we're quoting, as you can see here, they haven't quite crossed at the number that we're quoting. We're just being a little bit more careful in terms of what we want to say about the precise number. So you can see that it's somewhat, at least you'll see a threshold that is competitive, and it doesn't degrade too much. Yes.
This is only for 4 logical qubits.
This one is just for 4 logical qubits.
Can you ask me anything about if I have configure circuit across more qubits?
I think you can probably come up with arguments that at least tell you a little bit about how it generalizes. I do agree that maybe you can't precisely say, oh, this immediately tells me that my 20 logical qubit circuit will have this exact error rate. But I think it still teaches you a little bit about what you might expect there. And one thing that we did do is, for example, you can vary the depth here. And you do see that the things are all consistent.
So this is averaged over different random 32 circuits?
This, I think, was multiple circuits, yeah.
So what was the worst case?
That I don't remember out of the top of my head, but I think the variation was not large. And also, again, we checked a different depth with just another randomly generated circuit. And the things, like basically you see results that are consistent with this. Maybe I'll give another intuition about why you might expect it to be the same. Essentially, it's a competition of entropy removal using your measurements and kind of, and like added noise, right? And so if you have a different circuit, if you're doing C0s and whatnot, the amount of noise that you're adding and the amount of entropy, like kind of this kind of thermodynamic balance is roughly the same. And so generically, you probably would expect it to actually be somewhat similar. Of course, the details could vary a little bit, but also I think you can actually also prove code distance in this setting as well.
But I mean, I believe the argument for maximum likelihood decoding, but I don't necessarily believe it for, like, say, hypergraph unit find or anything like that, because it's very graph dependent. So
yeah, for a specific problem, definitely it needs to be seen. Yeah, I would maybe say that it's not like obviously clear that it will be exactly the same, but I think that it's also kind of not unreasonable to say that heuristically it likely will be similar. Yeah, I think Mike, you had a question. Okay. Great. Okay, so we can also look at kind of the actual space-time volume that you're doing per logical operation. And here what you see is that as we vary the number of rounds of C0, because you're adding these rounds of syndrome extraction, your space-time volume is going up. So here maybe I should mention, what we do is we have a target logical error rate, and then you can optimize the number of rounds of C0 you do to minimize the space-time volume, right? Really what we're trying to do is minimize the resources to run the given circuit that we want to hit the target logical error rate. And because you're adding in these extra rounds of syndrome measurement, you're really paying a lot of cost when you try to do these extra rounds. That you kind of, as long as your threshold isn't getting affected too much, you won't get, you maybe slightly increase the distance for the few rounds, but that's kind of a polylog overhead. Yeah. We're following them with the same number of rounds, so also 1 round. Yeah. Yeah. And so really, I think it's kind of an interesting balance between the amount of information that you're taking out and the amount of kind of errors that are added in. And I think it's interesting that we do indeed find regimes where you are actually potentially saving these factors of D. So with these, I think there are still a lot of questions. I think Shruti hit on a very important point, which is that in practice, when we're decoding these, they are going to be pretty complicated problems. So how can we actually still maintain the performance at large scale if we're trying to do something in practice? I think that's still an open question. And I think it's a very interesting question for people to think about decoders and to see maybe whether there are decoders that either can improve the practical performance or you have better guarantees about them. In our case, the kind of the most likely error decoder, that one in principle probably has exponential runtime. And the kind of union find, in principle, it's polynomial, but then you also kind of might suffer from error rate when you try to do it practically. Yeah. I don't remember out of the top of my head, but I guess we can maybe take a quick look at this. So these, I think, are the same code distances. So at least on this graph, I would say the lines kind of look parallel, but again, this is not like, yeah, it's something that requires more analysis for sure. And this line is most likely error, so I would expect it to still have the distance. But I guess we can check more carefully. That's a good point.
I guess
yeah.
So theoretically, I want to do nothing.
Mm-hmm.
I have to do D-rounds. And what you're telling me is now that I'm doing something, I don't have to do D-rounds.
So I would say even if you're doing nothing, maybe you shouldn't be doing D-rounds necessarily. Right?
But you can always show that there's a time-like error, which basically will connect the boundaries of do less than Q or 2.
So I think at least in this case, you have a deep circuit, right? And you kind of absorb those D-rounds into this. And I think it's an interesting question in an actual algorithm or maybe a different setting, what it looks like, right? So I would say this.
Yeah. So in that case, have you done that basically? Like, I mean, that's a good that's, I think, a nicer example is to like shrink the circuit size.
Yeah, this is something that we're also kind of interested in looking at. Yeah, so it's a great question. Yeah. Okay, so I think there's kind of this question of speed and accuracy here, which is indeed a little bit more challenging. And I should also say that maybe eventually, because our decoders can't keep up, you kind of do choose to do a little bit more rounds, right? Maybe the reason that we're not doing this super fast is actually not because our error rate can't keep up, but more because our decoders maybe like we want to partition it into smaller blocks. So I think it's definitely still like a very kind of open question. And I think designing the decoders, also thinking about real-time decoding, I think there's been increasing work on this. That'll also be very interesting, and co-designing it with the algorithmic context as well. Okay, so I'll kind of now move a little bit back into talking about the model that you might want to have for these quantum computers again, and kind of briefly comment also on maybe what the future systems might look like. I should emphasize that the technology is still very rapidly developing, and tomorrow's systems might look very different from what you're seeing here. But just to kind of give you kind of a somewhat working model of maybe what we currently have, we have access to hundreds to maybe low thousands of qubits. You have pretty high fidelity gate operations with long coherence times, and you can do these parallel moves in a very natural way. Also, you have access to some amount of mid-circuit measurement and feed forward. And I think there's some interesting analogies that from kind of the CS side you might think about with like a classical RAM, and kind of bringing it in and out. I think there's actually also interesting parallels with like for DRAMs, you actually need to do these refreshes. So it's actually quite interesting how some of the parallels might go. So I guess this is kind of a slightly more microscopic view of how some of these parallel operations actually look like. I'll maybe just very quickly go through some of them. Since this is recorded, you can kind of watch it later if I'm going too fast here. But you have sites that can contain 0 or 1 qubits. You have some fixed sites. And although I was assuming they're 2D rectangular earlier, this one you can really assume to be quite general and arbitrary. So that already gives you some degree of freedom. Then you have these movable sites. These, because of the current hardware constraints, you can only do in parallel in these kind of rectangular subarrays. But actually, a subarray also doesn't have to be completely filled, right? So you can have kind of some sites that are empty, and we'll just be picking up kind of these free atoms and moving them. When we move them, the rows and columns will move together, but a row cannot move past another row, and same for the column. This is because you might expect them to maybe collide, and so it's something that might not be true in the future, but at least at the current stage, that's what it is. We've already discussed this quite a bit. You can kind of take atoms, drop them up in different types of traps, and then now they'll be, say, in a static trap. And so you can kind of do these transfers, but that is something that currently has 0.1% costs. I think we're pretty optimistic, as we already mentioned, of reducing that, but that's something that is also something to think about when you're designing things. For the gates, we've seen a lot of great work, both from the kind of the community that we're in, but also from other people. So single qubit gates nowadays are routinely in the 3 nines to 4 nines range, and they can kind of be quite well parallelized across the system as well with these same techniques. We have 2 qubit gate fidelities that are kind of on the order of these 99.5s, but you do have kind of right now these parallel constraints where you're applying the same gate. Maybe that's not a big deal for error correction because we're usually anyway doing the same type of CZ or C0 gates, something to think about. And I think one nice feature about this platform is that the noise sources are relatively well understood. And also, because it's a relatively clean system, you can kind of think about really looking at it and then designing and adapting. So there's very nice work from Shruti and Jeff Thompson of thinking about tailoring the QEC codes towards maybe the noise characteristics that you have, either erasure, biased erasures. And we also, I think both in our work, this is kind of a error breakdown from our simulations in this high fidelity gates paper. I think there's also some very nice tables in other work from, for example, Jeff's and Manuel Andres's lab, where you can kind of look and really break down the detailed channel. And these I think will continue to improve as we push to better error rates and as we better understand these error models. So really programming a neutral atom quantum computer really looks like you kind of have all of these different toolboxes, and you kind of utilize a lot of control parallelism, and you can kind of do pretty complex circuits nowadays. But I want to return again back to this question of what is really enabling these complex experiments that you saw, and why really kind of maybe for many people in the community, it perhaps came a little bit of a surprise as to suddenly why people are suddenly doing such complex things. And I think this is also mentioned in Dolev's talk, where really when you think about it, the amount of control that you have for these systems is just very different from when we're looking at a classical computer, right? For a classical computer, you have billions of transistors and maybe on the order of 1,000 or so external controls. Whereas for the current generation quantum computers, you have typically, say, 3 wires per qubit, and this means that for a 50-qubit experiment, you're looking at hundreds of individual high-performance controls to control and manipulate the system. In the experiments that we're doing, and this is, I think, a large part of why even many of these relatively small academic labs with like 5 or so people, like in the Harvard experiment, we can still do a lot of these very complex things because the control is so simple, right? We don't need a team of programmers to go and kind of like write tons of software and like hardware engineers. I mean, eventually we probably will and do want to do that. But right now we're at the stage where there are still scientific discoveries, and both on kind of science and on, to some degree, even on error correction fronts to be made. And so here really kind of one wire controls one AOD, and this entire circuit, because we structured it in a way that utilizes the parallelism, we're just using these kind of in total like maybe 5 AWGs in the lab compared to like hundreds in many other platforms. And so really with this, we have these features of non-local connectivity and this kind of parallel efficient classical control that allows one to do very complex things. Yeah.
So it's like a not neutral atom person. Yeah. The thing that was surprising to me was not the number of qubits, but the sudden increase in 2-qubit gate fidelity. And the description of the 2-qubit gate fidelity when Bill was talking, that didn't seem that new to me. So what was it that made the fidelity go up so much?
I think this is again an example that the community just didn't have the patience to go and like hammer it down. I think so, and then of course on the technical front there were some innovations. Kind of there was the high laser power. That was kind of a big thing, and I think it will also be exciting to see for some of these other neutral atom qubits as they increase the laser power. I'm sure they'll also like do much better. And then also there were better cooling schemes that were implemented, and then also the gate design I think actually contributed quite a bit, like kind of using this time optimal gate that is a smooth pulse that gets rid of a lot of transients that we didn't explicitly characterize, but were probably plaguing our previous gate.
And then what do you, using your current smooth gate, what do you think the fundamental limit is versus technical limit?
Yeah, so I would say, I mean, people typically think that 3 nines is something that is achievable in these systems. Going to 4 nines is probably hard, I would say. So ions can, I would believe if ions can go to 4 nines. I think for neutral atoms, that's a little bit hard. But maybe there's creative ways. I mean, if you have like these erasure things, then your 3 nines is actually maybe more like 2 nines even, right? So yeah.
In the previous slide, is the individual addressability of physical qubit not necessary at all?
So there definitely are operations that you want individual addressability. And we do have individual single qubit rotations as well. Right? We can do single qubit gates. So kind of most of the time you want the parallelism, but you also do have the freedom to do the individual movement.
For that, you need the number of controls should be actually a number of physical qubits?
You're doing them at different times and at different sites. So you can also parallelize a lot of that, potentially. It is an open question as to how you actually parallelize, but I think it is possible.
So if you increase the power, I think 10 times to get to 99.57% fidelity. If you want to go to 3 9 fidelities, how much more power increase you would need? And if you increase the number of qubits to like thousands, will that also proportionally increase the power? Or?
Yeah, that's a great question, and I think that's something that does need to be kind of solved in these systems. Certainly right now, I think we're probably more limited by things like transients than necessarily our power right now. And I think there is still quite a bit of room also optimizing like top hats for the atomic physics. These are all things that can be further optimized. So I think we are optimistic that with these schemes, you can certainly get kind of good gates on like at least small system sizes with probably free nines. With larger system sizes, I think it is an interesting question that still needs to be. So I don't know if you have any more comments than that.
Oh, I agree with everything you said, and I'll clarify the record on one thing, which is that we increased we got to 99.2 or 99.3 just with the exact same laser power, and then the 99.5 we're not even utilizing all that extra, like back to 10% power. So actually the main thing was just repeating it, as very correctly said.
Okay, so of course, we're also interested in kind of like what limitations there are, right? I'm sure you'll also like to hear that. So we obviously need better qubits and more qubits. I think this we've already touched on. One thing that has also been kind of discussed a couple of times is the fact that here we're actually not doing a continuous operation. And so for us, actually, our optimization and what we choose to do is very informed instead by the space-time footprint rather than the space footprint like you typically might be thinking about. That being said, all of these are being actively tackled in the community. A year ago, the same discussion was with mid-circuit measurement. Since then, we had 5 different approaches, all of which seem to work quite well. Here, we've already seen 2 papers starting to address this, some from atom computing, some from MPQ. And so I think it's very exciting, and I'm sure we'll see more of this. But really, I think kind of as we think about these large scale, we're still very far, right? I mean, we brought these physical error rates down a little bit, but we're really looking at 10 to the minus 12 or 15. And so we really need all of the breakthroughs that we can. And it's not something that we should view as a static technology. This is just a snapshot, and we need to be creative in thinking about what we can have. So I was asked to kind of give a possible model for a next generation quantum computer. I don't know what it will actually look like. So I'm just putting something that might appear in a few years, hopefully will appear, I guess based on the QuEra roadmap. So there's 10,000 qubits or so, hopefully kind of very high gate fidelity operation on them, continuous reloading, mid-circuit non-destructive measurement, kind of many of the shortcomings that you see right at this snapshot. I think people do have pretty concrete ideas to address, and it'll be interesting to see how it develops. But I think it's also interesting. Oh, yeah.
So would you say what the total number of gates you formed for this number of qubits? Total operation.
I think the hope would definitely be that you get into a regime of 1 million or so gates, but that really depends on a lot of details, and whether we'll get there or not is a question. Yeah.
Sorry, I haven't seen the QuEra roadmap, so I'm not sure. But so this, when you say mid-circuit measurement,
yeah,
are you still going to do 1 measurement on 10,000 or two measurements on 10,000 qubits, or will it actually be?
The hope would be that if you're really operating continuously and then like you're trying to do 1 million gates, then you'll definitely be doing many rounds. Yeah. But I also want to kind of mention that there's a lot of exciting new hardware functionalities and ideas. The neutral atom community is very vibrant. There's new atomic species a lot of people are working on. There's kind of new optical hardware, like kind of integrated photonics or lattices. There's also cavities of kind of networking, and you can think about maybe how you actually distribute the algorithms. And so I think there's a lot of interesting kind of directions to think about. And really, I think what I want to say also is that, especially for theorists, you should keep the kind of aspects that we have in mind. But I think it's also very important to think, just even regardless of those constraints, where can I get a 10x improvement, right? Like if you have ways of getting a 10x improvement, people might be inspired to then think about ways that maybe it eventually becomes a 3x improvement in practice, but it will be inspiring. And I think we've seen this example with the LDPC codes, where 10 years ago when it was, actually I guess it was 15 years ago when it was proposed, these hypergraph product codes, I don't think people really had any of these types of considerations in mind, but eventually it still inspired work on the side of really implementing. And I think maybe if you want one thing to keep in mind as you're thinking about building your own model, I think this control parallelism is a key aspect And you can define what you mean by control parallelism, right? It doesn't have to be the sense that we're talking about, but maybe that inspires someone to make a different type of device that has a different type of control parallelism. So we learned a lot from the community. I think Dolev already showed this slide. But I also want to emphasize that these same lessons, oftentimes kind of what we've learned isn't really unique to our system, right? Like we've seen that structured non-local connectivity can be very powerful. And the same ideas, I think, also actually apply to trapped ions, to quantum dots. I think people are starting to think about these as well. There's also kind of these very nice works that Ted Yoder talked about. And also, I think parallel efficient classical control doesn't have to be unique to this platform either. If we think about superconducting qubits, I was told by my friends that the per channel cost is $10,000 per qubit. If we think about 1 million qubits, that's $10 billion. I'm not sure if the companies are necessarily willing to shell out that amount, maybe, but I think it remains to be seen. So I think there definitely will be a point where even in these other systems, you also think about how you can really kind of efficiently do these control. And I think it will be interesting to see how kind of other communities come up with approaches to try to address this. So in summary, I kind of told you a little bit about some of our perspectives on where the error correction is today and where it might be tomorrow. And I'll just flash this slide again from Dolev, that there's really a lot of things that we can think about of co-designing these systems, of thinking about the error correcting code, but also about the algorithm and the native hardware capabilities today and tomorrow. And it will be very exciting to see where the field develops in the next few years. So with that, I'd like to thank a lot of the great people who have been involved in this. This is kind of the team for the logical algorithms experiment that Dolev showed. And then correlated decoding, Maddie and Chen were kind of mostly taking the lead here. And then for the LDPC experiment project, it was a great collaboration with Liang Jiang's group, and in particular, Qian and Pablo really spearheaded a lot of the kind of hard numerics work that were in here. So with that, thank you very much, and happy to take questions.
I have a question about the primitives. So you said that you can move a block of qubits, but on some of the movies I saw that you could move like every other row of qubits or every third row. Can you actually do it? Is it part of the primitives?
Yeah, maybe I should clarify that the rectangular subarray doesn't have to be contiguous. So you do indeed, like you can basically pick up whichever columns you want. And this is, yeah, very easy to program.
Can you do it like in a checkerboard pattern?
So a checkerboard is not a product anymore. So that is not so easy to do. But yeah, I guess I also wouldn't rule that out. I mean, people are creative with their optical tools. Currently no.
Allows you to do like every other row,
yeah,
or every third row, or every fifth row.
Yeah, exactly.
If you just rotate the AOD 45 degrees.
Exactly. See, we already have some creative optical designers. Yeah, that's probably how I would do it. Yeah.
Yeah. So, if I understand correctly, the current scalability of your platform really depends on transversal gates. This can be collective control. Or, transversal gates. But to perform universal computation, of course, what you need really is transversal gates cannot be performing computation. So, but if the scalability really needs this kind of collective control, this might be a little concern, for universality. So there's some way that you have in mind to overcome this kind of scalability for non-transversal implementation gates.
Yeah, I mean, I guess in the usual setting already, most of the time people are kind of, for example, these magic state distillation approaches, right? You kind of have just a little bit in one place, and then the rest of it, you kind of still do your regular Clifford operations. So we can kind of imagine doing something like that as well. I don't view it as a particularly strong limitation, but also at the same time, it would be interesting to think about. I mean, you saw the A32 code. I think people have very interesting ideas of seeing how they generalize and whatnot. So it'd also be interesting to see different approaches to that as well.
Maybe one last question. Okay, I wanted to thank